we're going to talk about the fundamental theorem of abelian groups. We're going to talk about what it means. We're not going to prove it. But basically, if you have a finite abelian group, you get that G is isomorphic to a bunch of cyclic subgroups of prime power order. So let's take a look. We're going to be looking to interpret this. So you can find it, for instance, in Gaussian. It's kind of complicated, but here's what it is. If G is a finite abelian group of 432, you just need to find out all the ways of doing 32 and fifth. So you could either have a cyclic group of 4, you could have a cyclic group C16 cross C2. Now these are different. This is going to have an element of OR32. This is going to not have an element of OR32. The biggest, highest power, highest ordered element is going to be 16 in there. So you can talk about the partition 4 plus 1. Right? A partition is all the different ways of writing 5. So 5 you could write as 5. You could write as 4 plus 1. You could write as 3 plus 2. You could write as 3 plus 1 plus 1. You could write as 2 plus 2 plus 1. You could write as 2 plus 1 plus 1 plus 1. And you can write as just a whole bunch of 1s. So that's what a partition is. It's just all the ways to kind of add things up. That's 2 cubed plus 2 squared. You could have 8, 3, 1, 1. If you just look at the exponents, break up the 5. A whole bunch of groups of order 32. What the fundamental theorem of a abelian group says is that you only get cyclic groups to play with. The cyclic groups have to have prime power order, and this is it. You can break up the 32 however you like. You could just put them all in one chunk. You can split into 2 that way. You can split into 2 that way. You can split into 3 that way, 3 that way, 4 that way, or 5 that way. But it's got to be one of those. So let's look at another example. 360. I can write that as prime factorization. 2 cubed, 3 squared, and 5. So again, we're going to look at the partitions. 3 could be split up into 3, one big chunk, 2 plus 1, or 1 plus 1 plus 1. 2 can be either split up as 2 or 1 plus 1. And then 5 is just going to be, that's really 5 to the 1. 1, the only way to split up is 1. So you have 3 options for how to split up the 2's, 2 options for the 3's, and 1 option for the 4. So there should be 6 total options. Let's take a look. So either I could put all the prime powers together, put all the 2's in one place, all the 3's in one place, all the 5's in one place. I can't mix and match with the 5's. I mean, you can do that, but the fundamental theorem of abelian group says it's useful to think about it as keeping the primes separate. All right, or I suppose splitting up the 3's or the... Oh yeah, by the way, oops. If you have a bunch of things of coprime order, that means that they just are cyclic. So you get a cyclic group of 360. I could split up the 3's into that. That's one option. So I could do that, and I get another group, splitting up the 2's. The 2's I can split up that way, and I can keep the 3's together, split the 3's up. Or I could C2, C2, keep the 3's together in groups of 3. But the key thing is, you want to think about this as, here are my 2's, here are my 3's, here are my 5's. Here are my 2's, here are my 3's, here are my 5's. Here are my 2's, here's my 3's, here are my 5's. 2's, 3's, 5's. 2's, 3's, 5's. 2's, 3's, 5's. And so if you know how to split up the prime powers, basically by using partitions of the exponent, then you can just break these up. So let's find, you can do this in your teams at home if you like, but how many abelian groups are there of order 54? How many isomorphism classes? Well, again, look at the exponents. You have exponent 1 and you have exponent 3. The only way to partition 1 is 1. But 3, you have 3 options. You could either have 2 plus 1 or those 3. So here you have one option, there you have three options, so you're going to get three possibilities. You're going to have a C2, because there's only two. And you could put all these threes together and you get C27. Or you could split the threes up into two chunks. Or you could recross 3-3. And those are really the only options. So you only have basically three types of abelian groups of order 15. So in closing, if you want to know about abelian groups, you really just need to know about direct products of cyclic groups of prime power order. And that'll tell you everything you need to know about abelian groups. That's what the fundamental theorem says.